Okay, everyone, welcome to day 2 of the virtual summer school. Today we're going to do some tutorials, demonstrations on how to access and work with images. And then at the end of the day, we will get to some collaborative breakout time where you all can form into small groups and work together on projects of your choosing. Don't worry if nothing springs to mind immediately. We can help suggest some ideas for you for that. These are the same links that were available on yesterday's slides, so I won't go through these, but just keeping them here for convenience. Right, so today, as I mentioned during the breakouts, those are meant to be sort of small group projects, explorations. So as the day goes by, sort of if anything comes to mind that you might want to work on and perhaps work collaboratively with some other attendees, you can make a note of that in the collaborative breakouts Slack channel. And we're collecting those ideas so that when we come to that session, we can form breakout rooms. And I think that's all I have for announcements for today. So we can just dive right into the tutorials, starting with Nandini, who's going to take us through Notebook 3A, which shows you how to display and manipulate images. So go for it, Nandini.
Can you hear me? Okay.
Yes.
I'm going to share my screen. Right. So since it's our first tutorial of the day, we're just going to quickly go in through and log in case someone is having issues with that. So I'm just going to log in with my Orchid because that works better for me. And so the link for this is data.lsst.cloud. I'm just going to put it on the chat just in case. Right. And so once we are inside the Rubin RSP, we are going to take a look at the notebooks. So we're going to go ahead and click there on the notebooks. We want to use the recommended server image. It's updated weekly. And please be careful because if you use an older image, sometimes you might have version issues with the notebooks. Right, and I'm going to use a medium container because just to be safe. And then we're going to wait and log in. So if anyone's having issues, please go ahead and post it on Slack or post it on the Zoom chat, and someone's going to take a look at that for you. This takes a while, and we're in. Let's work this on. All right. And once we're here, we have these, all of us should have these 4 folders, and we're going to go inside the notebooks and the tutorial notebooks folder. And here we have all the notebooks that we want to be looking at. Today, we're going to look at 3A, and then later on, Jeff will talk to you about Firefly, 3B. So I'm going to go ahead and double click on that. And let me know if the font is large enough. I can make it a bit larger. Hope that's better. So this is beginner level notebook. So it's great for getting a feel for the image products that we have, a couple of them that we use the most. In particular, what we are going to do is we're going to query using the butler. Oh, you'd like me to widen my screen? Okay. Is that better? Oh, right. Yeah, sorry. I was just keeping an eye on the chat. Okay, that's better. Okay, so we're going to query using the butler, CalX, which are the single exposure images, and also the coad image stacks. And we are also going to look at making RGB multiband images and querying the photometry object tables. The packages that we're going to use are the ones that at least some of them were introduced by Jeff yesterday. So we're going to use the AFW display, which is an LSST package for displaying all the images that we're going to get. And we're going to use the butler geometry to define the geometry of what we are querying, and AFW.image to take a look at image stacks. We are going to import the packages that we want. So it's Shift Enter to execute the Python cells. And we're going to go ahead and import all the things that we want. I think you're familiar with all of these. Perhaps LSST.John, I don't know. Yeah, all right. So what we're going to do is define a few functions and parameters that makes it easier for us to query these images and look at them once we are in. The first is to remove a figure, because as Fabio mentioned yesterday, it's always good practice to remove our tables and figures so that we are not overloading the server with a lot of active stuff going on. So we're going to go ahead and that function makes the figures and then removes them when we need. And then we're going to have a definition of the cutout coad. So somebody asked a question yesterday that can we only query by tracked and patch and visit? So yes, but what we can do is we can also understand what visit or tracked or patch we want based on the ARIA index that we have of the object that we want to be looking at. So using the butler, it's possible to go ahead and define the geometry of the sphere point using ARIA index. So in degrees, we're using, that's the unit we're using right now. And we can also define a cutout size, which is in pixels. And we're going to get the sky map using the butler. And then we're going to go ahead and using that sky map, query the track and patch in which this ARIA deck lie. And once we have that, we have the X and Y point using the WCS of that tract. And we can convert it to pixels to define the center of the image. And using the B box, we determine the edges of the image, which is the cutout size. And then we can go ahead and query that image using the butler. So there are different dataset types, and what we're going to use is the deep coad for this one. And we have queried the ID and supplied the parameters. So it's going to return the cutout image at that ARIA deck of the defined size of a coad over there. So we're going to go ahead and define that function. The other function that we're going to use is we're going to define is to cut out a calyx image. So calyx are single exposure images, which are, so this is slightly different, a different way of querying. So we are going to use visit and detector to query these images. And again, we're going to find the ARIA index, define the cutout size, and using the butler, get the data ID for that visit and detector. And then in the same way, we're again going to use the butler to get that calyx image out, and then we're going to display it later on. So we're going to go ahead and define that function as well. Right. What we're also going to do at the end of the tutorial is to make RGB images using multi-band images that we will query. But I'm going to come back to that. I'm going to circle back to this towards the end, after we have had a look at the coad and calyx image, so that we can have a better understanding of what's going on there. So we are going to use AFW display, so LSST.AFW display to display our images that we query, and we are going to go ahead and initialize that with the matplotlib backend. And we are going to set our plot style. These are just preferences for plotting. You can go ahead and modify them. These are the parameters that we're going to be using. Again, as Douglas mentioned, I think yesterday, if you want to retain the changes that you've made, you should copy this notebook in your own data folder and then make changes there so that you can retain them. And then what we're going to do is initialize the butler with the data set DP0.2 and the collection, which is the latest one, 2.2i runs DP0.2. And once the butler instance has been initialized, we can retrieve the calyx or the coed images. To retrieve the calyx, we need to be telling the butler which visit and CCD we want to view. And to do this, we can define dictionary with the required information. So we're going to go ahead and do that. And right. So once we've obtained the data ID, using that, we can ask the butler. So we can do butler.get using the calyx. So since we're querying the calyx images, we are going to input that and put in the data ID. Right. So the calyx that is returned from this execution of the butler.get is an exposure Python object. They are image stacks, and they will also have a variance image, a bit mask image, and key value metadata attached to it. And we're going to go ahead and use AFW display to look at the image and the mask out of this data stack. And since you are on the notebook, I presume there's also more information on what else you can access and visualize for an exposure. So to take a look at the image that we have now queried, we are going to use matplotlib.pyplot and initialize a figure. And as I said, once we have taken a look at the figure, we always try to remove it so that it's not lying around doing fancy things in our storage. And that is our first calyx image. And we have set here the display scale as A sin H and Z scale. You can go ahead and modify that as well. And we have plotted this in sky coordinates. Sorry, we have plotted this in pixel coordinates. So you can see here the pixel coordinates go from 0 to 4,000. We could also use the AstroPy WCS package to, so Python's AstroPy WCS package converts these pixel coordinates to sky coordinates, and we can display the image in RENDEC instead of pixel axes. And we can go ahead and do just that. So the next section, it takes this image and converts it using the WCS to get RENDEC values. And here we have it. So instead of the x-axis and y-axis being pixel values, we now have RENDEC in hour, minutes, and seconds for the rate ascension, and degrees and minutes for the declination. All right, so we've plotted an image in two different ways using afw.display. And as I said, this image stack also has the mask plane. And we're going to go ahead and take a look at how the mask plane looks for a calyx image. To do this, we are going to initialize some colors. Right. To do that, so each mask image has bitpix values, which are set by colors or by powers of 2, which gives us information on why a pixel has been masked. So certain colors, as you can see, so yellow would be a suspect pixel, an edge pixel is yellow, and a saturated pixel is green. And so each pixel in the mask will have a certain color based on why this is a bad pixel or should be masked. And if we plot this side by side with the image plane that we queried, we can see exactly what's going on. So we have used a linear and z-scale image to plot our calyx image right here. And then we've gone ahead and displayed our mask plane on the right here. So you can see that for this image where you have a large star where there might be saturated pixels, there is a corresponding mask pixel, which is color coded according to what we expect to see there. All right. Are there any questions in the meantime?
Yes, so there's one question from Matthew Weisner.
Mhm.
Fabio also addressed it, that mentioned that it will be covered tomorrow, but the question is if there's a way to know the available visits and detectors for CalApps that cover a particular RA attack.
Right. So I think, yeah, so as Fabio said, there is a way to query this with the butler and take a look at it. You can also take a look at all the different data set types that exist. And yeah, so Fabio will go and so basically using the butler.registry, you can go and look at all the different data set types. And also you can, again, using the butler query, what visits and IDs exist for a particular location in sky. Okay. Okay. Let's go ahead and look at another plane in the CalExp image that is also there in the data stack. It's called, so when we are querying the image, we are using calexp.image, and when we are querying the mask, we are using calexp.mask. But there is another plane in the data stack, which is called calexp.maskimage, which allows us to see an overlay of the two planes that we looked at above. And that gives us a better idea of which pixel where, right? So I'm not great at looking at colors visually. However, you can see that here, these are the pixels that should be saturated. These are probably pixels which have certain kind of features in the CCD and have been blocked out because of that. And then these kind of look like lavender to me, and I'm not sure what code those signify. It's probably a combination of two colors. So that's an interesting thing to find out later on. All right. So to look at the mask in more detail, we can set the color of the detected mask plane to a certain color that we want, and then change the opacity and pass the whole CalExp to our display module instead of only the calexp.image. And this will help us take a look at the mask in a bit more detail and sort of explore what's going on if we want certain, right. So you can see less of the star, and you can see more of what's going on with the mask over there. And you can play around with this a little bit. And let's say we put it to 60 and see what happens. And just to make sure we are removing the figure every time we generate one. Right. So that's with the mask transparency of 60. And you can see way more features in what's going on there. So you see that green line that was not visible earlier and right over there. And you can play around with these parameters and refer back always to the key right here to see what is being masked with which code. Okay. All right. So what we can do, so we have used a certain section of lsst.aw.display, but we can also print all the different methods that are available to us from lsst.aw.display, because it's a very powerful tool. And we can see that we can use, so what we've been using is mostly MTB, but we can use, and we used set default mask transparency, and we have used set default backend in the past to set it to matplotlib. But we can play around with all of these methods, and we can get different kinds of displays based on what we require. If we want to have more information regarding any of these, the source code is available, and you can go and take a look at that. And if you want information or help for any one of these particular methods, you can go ahead and do help display.scale. and it shows you what parameters it takes and what you can expect from these methods. All right. So now we are going to extract a cutout image using the method that we defined earlier. So before this, what we were doing is that we were giving a visit and an SCCD ID to the butler and getting the calyx. Right now, what we're going to do is use RANDEC to, or give pixel coordinates and then get RANDEC and then use that to get a calyx cutout. And then we are going to go ahead and get a coad cutout. The first thing is to, we have these pixel coordinates, so 2250 and 700, and then we're going to use the calyx WCS to convert these to RANDEC and go ahead and print them. So that's what we have. And what we want to do is we want to use the same visit and detector ID that we used in the previous section. And we're going to use the cutout calyx function that we looked at in the beginning. And so we can, since it's a function we have defined, we already know what it does. But if we want to take a look at what it does, here we have it. We can print it out with using help and then see what kind of parameters it takes and what image it returns. And so we are going to go ahead and initialize my cutout calyx because we want the masked image that comes out from cutout calyx. And then we want to have a box size of 301. And we already know the RADEC and visit and detector that we have. And so we have used the butler inside the function cutout calyx to get a masked image. And once we have it, we're going to go ahead and use AFW display again and display it using the .mtv function that we now love so much. And here we have it. So that's our frame. It's a 300 by 300 box. And once we have displayed it and we have looked at it, we can go ahead and look at other features, or we can go ahead and look at other cutouts. And then at the end of all of it, what we will do is delete the image that we have generated and all the details that we have queried and generated, because we want to be using some of these variables later on. And we don't want them to clash with the variables we've used earlier. And once we've had a cutout calyx, we are going to look at a cutout of a deep coad image. Right, so we have a data ID using tracked and patch and band. And we are using a dataset type deep coad. So I think Fabio will also address this in the butler. So using butler.registry.dataset type, you can also see what other dataset types exist. And we are going to query the coad using butler.get and plot it. So this is what we do, which is the most basic thing. So if we know the tracked and patched and what band we want the image in, we can directly query the coad and look at the galaxy cluster. Right. So what if we don't have the tracked and patch? Right. We're going to use, if you remember, the function that we defined in the beginning, and then we can use that to get the tracked and patch and then display the coad. Before that, we can take a look at what WCS is there for this. So this is what we will use, for example, if we have pixel coordinates, this is what we will use to convert to the RANDEC coordinates and back and forth. So we can do pixel to sky, but also sky to pixel. And we want to use our favorite function, which is cutout coad. And so we're going to go ahead and look at what it does using the help. And we can see that in the same way as for cutout calyx, it takes all these parameters and it returns the masked image like we had earlier. Right, so we have the RA and deck, and we don't have the tract and patch, but we're going to have cutout coad do that for us. And we're going to send it the butler RA deck band value and the data set type that we want. And the box size, we are using a slightly larger box size than the calyx. So we are using 501 by 501 box. And we will go ahead and display that. So it's a segment of the image that we looked at earlier. So it's a close-up of one part of it. And it's fantastic. Love it. Okay. Once we have this image, we want to know in this crowded field what kind of sources we have. And what we can do is query the catalog sources and overplot them on top. And this is something that you looked at already using tab, how to get catalog data. And then this is a sort of application of how we can integrate that into our image display modules. Right, so we have our WCS, we have the box sizes, and we don't even need to define it by hand. We can use the get width and get height, and defining each corner, we can then ask the tab service to get us all the objects with RA coordinates within this box size with the tract and patch values that we queried from the catalog of DP0.2 DC2 objects, where these RA points are contained within a polygon size that we have defined with the corners just before this. And we have the results from the step query, and we want to see how many they are. So we are going to use ToTable to convert them to an AstroPy table, and then sort of print it out and see. So we have the ID of the object, we have the RA coordinates, but also the pixel coordinates, and we have the tract and patch as well in which these appear. Right, so we are going to use something nifty, which is called display buffering, so that we avoid redrawing the image after each source is plotted. So it holds the image in the buffer and then overplots each object on it. And if we take our table of objects and go ahead and plot every source with that we have X and Y coordinates for, with these red dots, and then circle it around with an orange circle, this is what we get. So our frame has all of these objects, and with and there are different ways of displaying the objects that we want. We can use crosses or O's. We can determine the size of those circles, and right. So now we know how to query a calyx, a coad, and how to query the tab for all the objects that are there in that frame and to plot them on top of our image. So, however, the tab catalog the catalog of objects that we queried is multi-band, and the image that we have is only in one band. So you will see that some of the objects that are there in the catalog don't really appear very prominently on the image itself. Right. So now we're going to go ahead and take multi-band images and make a composite of them and make an RGB image. So we are going to go back up to the function that we did not talk about in the middle. And we're going to go and take a look at that now. Right. So the function is called create RGB. It takes an image's input, and then it takes multi-band images from different filters and assigns them RGB colors as you have as you instructed to do, and it takes these multi-band images and it scales them according to, so what you can do is either scale them equally so that they have 1, 1, 1 weight, or you can scale them differently with different weights And this will determine the amount of red, green, and blue that you have in the image based on the band that you have assigned the red, green, and blue color to. And we are going to use this function called make looked on RGB, where it takes the three different band images and makes a composite of them and returns an RGB image at the end. And we can take a look at directly how that looks like. So we have executed that cell. So now we have defined this function, and we can, sorry for scrolling very rapidly back and forth. Okay, here we are. So we can query the butler for coads in G, R, and I bands. And that's the three bands that we want to make composite into our RGB image. Instead of 501, now we are using 701 pixel cutout. Size of the cutout is 701 pixel by pixel. And we are going to make an array of the three images that we have cut out, and we are going to call it coads. And we are going to define them as a multiband exposure object using this function from exposures, and going to assign the filters that we cut out them from, which is G, R, and I in sequence. And once we have this composite of three band images that we have, we are going to go and run it through create RGB, first with no scale. And then we're going to go ahead and create the RGB with different scaling for the G, R, and I. So different weights for each of the images. And we're going to have an original RGB image and a scaled RGB image. And we're going to go ahead and see how they look differently. And that's it. So this is the original with 1:1:1 scaling for all of the three. And this is the rescaled version where we have assigned different weights to the different colors. If you would like, we can also go ahead and do something strange. And then there. We just have different colors for the different bands. And so you can see that some objects which are more prominent in certain bands then don't appear as prominently in the other bands anymore. And so if you change the scaling, you can see very clearly which objects are more red and which objects are more blue. That's it. That brings us to the end of the tutorial. And there are some exercises at the bottom. There are other exercises that have been suggested by Alan, and we might pick up one of those for the breakouts later on. You could also go ahead and try and overplot the catalog on top of the RGB images and see how that looks. All right.
Thank you, Nandini. Hey, I was wondering, I don't think I've seen this, but you could, it'd be interesting to have something where you could blink on the different masks, you know, like you're showing these two, but it'd be nice to have it on the same plot where you could vary the colors and actually watch stuff appear and disappear.
Right, so I definitely think you can do it with Firefly.
Yeah, oh yeah, that's a great idea.
And so Jeff is going to talk about that, but I am not sure if AFW display can do that because it's not interactive, right?
Right, right.
I don't know, is it?
I'm not sure.
I don't think so, but it seems like it'd be a really good tool.
Yeah, I think Firefly is really great for that kind of stuff. Like it's really interactive and you can see a lot more with the images. Thanks, Bob. Any other questions, or we can go on to Jeff's tutorial and see more exciting interactive versions of what we can do with these images. Oh, how I made it purple? I just changed this. I think it was 0.5 and I made it 0.2 and so that's the G, and I made the other scale to 0.1, and yeah, that's why it's purple. So it's just weighting the G and R differently in the composite. It is a pretty color, I agree. Okay, so I will close this tutorial, and if you have other questions, please ask them on Slack. And over to you, Jeff.
Great, thanks. Yeah, we will encounter the answer to Bob's question in just a few minutes with how you can do this. You can explore and manipulate the mask plane a little bit more within Firefly. Let me see if I can find the right window. There we are. Okay. Here we go. So yeah, we're going to go through now a more interactive way of looking at images and working with images. So this is notebook 3B, if you're following along. It's called Image Display with Firefly. You'll see what Firefly is in just a moment. Yeah, all the screen real estate we can get here. So let's see if this makes it larger for you all. Okay, so this is basically just going to be a demo of Firefly and some of the things you can do with it. Visualizing the images, again, overlaying sources on the images. So this is just showing you different ways of interacting with images that you might use, you know, you might use something different when you're in sort of the exploring mode. And then once you've got your results, maybe then you want to use a more static plotting method. So so Firefly, if you're familiar with other image viewers like DS9 or things like that, Firefly is analogous to those. It's something that you can launch and work with directly in the Science platform. And so you'll see that very soon. As usual, we will use AFW display, and we will need the butler, so we'll import those. And basically what we do to access Firefly is, instead of, you may have seen it go by a couple of times, a line that says AFW display set backend, and you set it to matplotlib to do static plots. But if you want to use Firefly, you'll see us just change that line, and that's all we have to do to send the images to a different display tool. So I'm not going to go through this part in detail, but you've seen this before, that for your CalX, the calibrated exposure, you need each one is uniquely specified by the visit and a particular detector that you want to retrieve. So we'll create that data ID for a particular one here. We initialize the butler. You're going to hear a lot more about the butler in tomorrow's sessions, but you get to see at least a little bit now. And then we will read in that calibrated exposure, that CalX, with that data ID. And there is a note here in the text pointing out that you could specify here the band like so, saying band :I as another dictionary entry, but that is actually redundant because the butler knows that this visit was observed in the I band. So you don't actually need to add that. This is unique enough to specify that image. Okay, so then we go on to we're going to use AFW display, as I said. And what you do here is, as I said, you just say, instead of set default backend to matplotlib, in this case, we are just going to set it to Firefly. And then you do this one extra step where you say, you may remember a similar call to this method AFW display within the plotting sections of when we were using matplotlib. In this case, you do the same thing, but now it's going to send it to frame number 1 of Firefly. And so you'll see what happens when I execute this. An entire new window opens up, showing me the Firefly display, and Firefly is ready. This is good. I'm going to show you a trick that you can do, and hopefully this won't make the display too hard to read. But with Jupyter Notebooks, you can do this with any windows that are open here. If I click and hold my mouse button on the tab for one of these windows, and then drag, you see the top half turns blue, the whole thing turns blue, right half, left half. So you'll see what happens if I drag that to the right half and then let up on my mouse button. Now I have these two images displayed side by side. And then if I want to go back to normal, I just click and grab that and then just turn the whole screen blue. And now it's back to the normal view. So hopefully this doesn't make things too small. If it's hard to read, let me know. But this way, if I put them side by side, you can see things instantly instead of having to toggle between the frames. Where were we? Okay, so we opened our Firefly window. You'll see more about what that does when we display an image. So remember, we grabbed that CalX. So again, we're using the same method that you always use with AFW display. MTV is the method that displays an image. So let's see what happens. Voila, we have an image. You can see it displayed, the multicolored mask display over the top of it. So each of those colors corresponds to a different mask bit. We'll explore those in just a second. You can, if you don't want that obscuring your image, you can change the mask transparency, as Nandini showed you a little bit ago. So it goes from 0 to 100%. So if I change it to 20%, you see it got more opaque. If I set it to 80%, it gets more transparent. So that's just the set mask transparency method. You can also set the scaling of the image itself. Here we're going to use this 1/8" scaling, and you can set the min and max. Let's see what that does to the image. We could do it. We could again use something like the Z-scale algorithm, which will scale it even differently. I don't think that did it finish. So notice if I mouse over this image and I use the scroll wheel on my mouse, I can zoom in and out on the image. And I can grab with my mouse button and pan around the image. There are also buttons for zooming in and out. But it's very simple to just use your mouse to explore the image. So here you can see that set of galaxies that we just saw in a plot a little bit ago. Okay, so now we want to get a little more detail about the mask colors. So we'll show you two ways that you can do this. One is you can actually get the dictionary of those mask plane colors from this method attached to the CalX. So you get you have that calibrated exposure dot get mask. And then once you get it, you just loop over those and print the mask name. And then you look up the color with this get mask plane color for each item, each named mask item. So when I do that, you see that we get, here, let me put this back to something more. Let's go back to this so you can see the mask better. Okay, now you can really see them. So you see here, the pixels that are colored red are, well, actually there are two things that are set to red. That seems like a problem, but some of them are crosstalk corrected, and some of them are bad pixels. You can see this big green blob that looks like it corresponds to, oh, okay, there are 3 set to green. That also seems problematic. We might want to change that. So those are either not deblended, that's my guess for this big blob, or this one you can tell is a bleed trail from saturation. So that's a saturated star, and those pixels have been interpolated. You can see, let's see, do we see something in here? Yeah, so you can see this is also this is a, looks like a cosmic ray that has been interpolated over. And in fact, yeah, you can see there's green on top of magenta. We'll come back to that in a sec. The other way you can look at that, besides just accessing it in the notebook, is to go to the overlay button in Firefly. So this button that has 3 images overlaid, and you see when you mouse over each of these, you'll get a tooltip that tells you what each of these does. So we want this overlays button. And now you can see that it is showing you each of those mask plane bits. The nice thing here is now I can say, okay, this is, we noted that there are 3 things defined as green. I can mouse over it and it will highlight which ones it corresponds to, or I can uncomment, or I can click on this and remove it from the display. So look, when I remove interpolated, now you see that, yeah, that pink or magenta thing was actually a cosmic ray that has now been interpolated over. So you can do that you can remove the detected bit. Now you can see the star, the outskirts of that star that is saturated in the middle. And if I zoom out, let's see. Okay, so you can see the red ones that's crosstalk pixels that have been interpolated over due to crosstalk correction, or corrected for crosstalk. So you can interact. You can also just make all of them go away if you just want to look at the pretty picture. There you go, and then just show all to redisplay them all. Oh, Douglas, I see your hand.
Oh yeah, yes. If you go back to the overlay display, you also have the colors. You can also click on the colors and change them if you want.
Indeed. So when you click where it says color, it'll pop up this menu. So if I say I want the not deblended to be orange, let's say, instead, I'll select that color and click OK. And now we have to go find those not deblended pixels. There we go. So that's that big galaxy that it was just too big for the deblender to handle. Let's see. Yeah, so you can see it's a set of a few galaxies. So those pixels were not deblended. Yeah, thanks for that, Douglas. Another way you can change the colors, you can do it manually like that in Firefly. You can also, so here we're going to go through and actually just change them from the notebook. So this is just doing the same thing we did before, where you go and you get the dictionary. But then we go here and we just change the not deblended to purple. So this is just using that AFW display set mask plane color. And when we do that, we have to do one extra step to get it to appear in Firefly. We have to have it redisplay. So we rerun that MTV command. When we do that, hopefully those not deblended pixels show up as purple. Yes, they do. Excellent. And so you can set those to be whatever colors you want. We have an example here of a colorblind friendly set where we're actually using the hex designations for these colors. So we actually just cycle through and reset each of the, you can see each of the masks we set to one of those colors that we defined in that list. So when I execute that, again, to make it show on the display, we have to execute this MTV command again. Okay, so now you can see we've reset a bunch of those colors. We can pull this up and see what all of the colors are that we've set. Okay, so now I'm going to reset them, revert them back to how they were. One other thing to note is we did this mask transparency before. If you just set it to 100%, that means it's 100% transparent. So basically, the mask is not showing when you do that. Right, that was the not deblended. I forgot. So here, we'll zoom in on one. So that one, when I execute this, it'll turn off that mask essentially there. So that's the equivalent of clicking in this menu, toggling it on and off that way. Okay, and we actually kind of already covered this part where you can manipulate the mask planes from this menu within Firefly. So we'll kind of move along here. We get to this fun part where first I'm going to make the masks all. Oops. I'm going to hide all of the mask bits here. Zoom back out. Oops, not that far. Okay. So now we're going to do the same thing that Nandini did, where we overplot the detected sources onto the image. And so we use the butler to retrieve this source catalog. And remember, this is the data ID we defined that specifies this particular image. So that gets the source catalog corresponding to the same image. And then we can just plot the length of that array just to see how many sources there are. Okay, we have about 2,500 sources. We can see what's in that table. Sorry, it's a little hard to read with all of the stuff on the screen, but you can see you have ID, RIDAC coordinates. You have a ton of columns here. You can explore all of the columns in the source catalog later. But what we want to do is display them on top of this image. And so we do a similar thing to what Nandini showed, where we want to use this buffering so that we're not re-rendering every time we plot one of them on top. We just say keep them in a buffer until you've rendered all of the sources. And then we just say AFW display dot to plot a dot, in this case of the form of an open circle that we define by this. And then we say, and we're looping over, notice we're looping over all the records in that source table. So you get the X coordinate, you get the Y coordinates, because we're going to just plot it in pixel coordinates here. This just specifies the size of the circle, and the color will be orange. So let's see what happens if I execute that. Voila, you have sources. I can zoom out and you can see that that all of the obvious objects, except for maybe the saturated ones, have a detection. Another thing you can do here, notice that it's hard to see the very faint objects. So again, you can change the scaling. Remember, we changed it from the notebook earlier, but you can also change the scaling from this menu within Firefly. So this, you can see this histogram looking button. It says stretch drop down, quickly change the background image stretch. If we click on that, okay, you can see we're doing the Z scale or 1/8" stretch. If we want a linear stretch instead, I can click this and it will rescale the entire image. And now you can better see, this, for example, this faint object you can see much more clearly with the linear stretch. So you can see that these circles do have faint objects in them, and you can experiment with the various options that are available to you here. Because depending what type of object you're looking for, we might want to use a different stretch for that. Okay, and then just to clear those objects, you just use AFW display.erase, and poof, they are gone. Okay, now real quick before we take a break, let's display a coad image. This is a single visit image. A coad, as you've seen, you specify a tract and a patch and the band that you want. In this case, we will do I band. And then you just say butler.get deep coad, and it'll take a second to get that. And we're also going to grab the measurements for sources in this. In this case, we're going to look for the forced photometry, which is after you've detected all the sources in all of the overlapping images, do you go and then you require a measurement at every position. So we'll get those forced source measurements. And then once those are loaded, we can display the coad first off. Okay, that has a whole lot of mask information. It's kind of hard to see that there's astronomical data there, right? So this is a case where you really want to use the mask plane. The ones in particular here that are really affecting this image, well, okay, you can tell there's something green. It's either saturated, interpolated, or inexact PSF. We'll try this inexact PSF. What does that do? Okay, you can see that there's a lot of green happening in that image. Another one that is really important here is the rejected. You can see that's due to the diffraction spikes from this extremely bright star. So we want to get rid of those. And the other one, I think it tells us here. Yeah, the sensor edge, because remember that if I zoom in, you'll be able to see this really clearly. That light cyan color is a bunch of linear features at different angles. That's because this is a co-editable of, I think, over 100 images. They're all at different orientations. And so this shows you where the edge of one of the detectors appeared. And so if you've co-added enough images, you've almost spread that over the entire image, which is good, but it's hard to see your image with those in the way. So so we can zoom out and see better now what the image kind of looks like. We can go further and just set the mask transparency to 100%, and now we get to see that gorgeous galaxy cluster hanging out down in the bottom of this frame. And finally, we'll just quickly plot sources on this. Because this is a really big image, we're just going to select pixels in the bottom corner, 1000 by 1000 pixels. Again, we're going to use the detect as primary flag that you've heard about a few times. And we're going to separately select things that are extended based on that extendedness cut that you've heard about, and not extended. So we'll do that. Oh, and one thing I have to add here is that the corner of this, because this is a patch that is a part of a larger tract, the corner coordinate may not be x, y equals 0, 0. So you have to actually go and get the bounding box of this, or get the corner coordinate. So you have to get that x, y naught, and then subtract it from all of the coordinates of the sources that you retrieve, so that then we're doing it relative to this corner. And finally, let's plot the things that are, in this case, that are classified as stars, as not extended. Okay, you can see there are not a whole lot of them in that region. And now all of the things that are classified as extended, so basically not stellar, is what we use here. That's what the twiddle is. It just means not the opposite of that flag. Those are all the things classified as extended objects or galaxies. And so you can see faint little sources in the centers of most of these. If we change the stretch, you can probably see more. Yeah, see, now you can really see a lot of these faint guys. And of course, those galaxies are just buzzed out because of the extreme stretch here. So anyway, so that that shows you the basics of how to display and work with images in Firefly. There's a lot more stuff you can do with Firefly, obviously, but that it gives you some basics. There are some other sort of exercises that you could do here for further exploration. But I think I will stop there and see if, I think I saw some questions passing by. I don't know if any of these have not been addressed yet.
Hey, Jeff. So there's a question from Nicholas about these tools from AFW display and if they're heavily dependent on the LSSD file structure. So for example, if you can use AFW display to display other images, like with HSC or something like that.
That's a good question. I think that I think they are dependent on working with Butler objects. So yeah, you would need to ingest your HSC data into a Butler, which you can definitely do. We work with HSC data a lot in testing our pipelines. So you could do that, but it's not just like you just pointed out the files. I think AFW display, I'm pretty certain sort of assumes things are coming from a butler.
Let's see, and then there was a question from Matthias, who mentioned that the kernel seems to be systematically crashing on section 4 about the display of the co-add image, but I think the answer might be changing the container size from small to medium. So I'm not sure if that's the issue that you encountered, Jeff.
Yeah, that's a note, a good thing to note. Yeah, the co-add images and the catalogs related to them are, because they're very deep, there are lots of objects in the catalog, as you can see just from this little part where we highlighted. So the catalogs can get pretty darn big, and the images are pretty large on their own. And so you'll see at the top of each of our notebooks, we always give the recommended container size. So if you encounter that and your kernel dies, usually the solution is it means your kernel ran out of memory and killed itself. And so you just need to reopen a kernel with a larger container size. Oh, and I should add, while we're on the subject, that here we are, tutorial notebooks. That if you want to know before you open the notebook what the recommended size is, on the tutorial notebooks GitHub page. Oh, I thought it was on here, but it's not. Okay, never mind.
Yeah, so there's also some interesting discussion that Vincenzo and Nandini were having, but if we should, wondering if we should move to break or.
Yeah, we should definitely let people go
Okay.
break. We've been going for a little while here. Yeah, what time? 10 after. Okay, so I think it's fine to go ahead and take 10 minutes, and we'll come back at 20 after the hour, and we will learn even more about working with images. So see you all in about 10 minutes. Hi, everyone. Time for us to return from a break. Oh, thank you, Vincenzo. Vincenzo just noted in the chat that the next tutorial, notebook 6A, recommends a large container. So if you want to follow along, it's best that you start with a large container so it won't die when you try and load a large image. Okay, so we are back. Our next session will include demonstration of notebook 6A, which is about interactive image visualization in a different sense of interactive, I guess, than the Firefly. So Douglas.
All right, let me share my screen. And I'd also like to thank Vincenzo for reminding folks that at this next notebook, you probably want to use a large container instead of the standard one, the standard medium container. I just posted in the chat. If you want to do a quick restart, I'll just add it once again since it got disappeared. There's a shortcut to restarting your server. If you go to the hub home address on data, you can stop your server and start it again. But I will just actually do this from just the starting point, your normal starting point. I'm already logged in. I'll assume you're logged in, and go to notebooks, and I want the large server. But the recommended weekly is definitely fine. is recommended. And so we'll start that up. So we've been using the AFW display. We've been using Matplotlib. We've been using Firefly. We'll look at another technique for interactive displays using HoloViews and Bokeh, or Bokeh. I'm not sure how it's pronounced. For those of you who were at yesterday's B session, we also looked a bit at Bokeh and interactive plots. There we're looking primarily at plotting tables of data, catalog data. Here we are, and that was looking at notebook 6B. Here we'll be looking at notebook 6A, and we'll be primarily looking at plotting images as in this morning's earlier this morning notebooks. So let's see. Okay, so let's see. You should have, so you want notebook 6A. I've actually copied all my stuff over into a separate directory. So I'll be running mine from here. So let's see. Okay, so we'll be looking at CaliXP. Those are the single, recall those are the single epoch those are single epoch basic exposures on the sky. And we'll also be looking at the deep coads after you've had several images over part of the sky, and you just combine all those images together into a coad. And we'll also be looking at source and object tables. Let's see. We do note it's not recommended to do the restart kernel and run all cells in this notebook. You know, sometimes you just want to run everything. we don't want to do, generally do not want to do it with this notebook because it does require, you're doing interactive stuff, and it requires user input at various points. I mean, you can do it, but you kind of lose the purpose of the notebook if you just do that. Just to note that we will do our usual package imports. I'll start that running. It takes a couple seconds. We'll grab some general imports, NumPy, Matplotlib. We'll also grab AstroPy. We'll grab the butler, and we'll also import some classes from the bouquet and HoloViews packages. And these are bouquet and HoloViews are in active development, and sometimes you're doing things and you want to and you hit an error, you sometimes want to know what the version is. So here we'll just print out what the versions are for those, or you need to look up documentation and see the appropriate documentation for that version of HoloViews when you are pulling your hair out, trying to figure out what HoloViews elements you want to use or options or whatever. I'm going to stay at this point, as I said at the session B yesterday for notebook 6B. I'm not a HoloViews or bouquet expert, but the nice thing about these notebooks is that you can you don't need to be an expert. You can there's a lot of information here that you just grab, cut and paste stuff from these notebooks into your own notebook, maybe modify to get what you want, and there's a lot you can do with just what's there. And then when you get better, get more comfortable with these, you can go and look at the documentation and figure out other things you can do. So I'm not a guru on this. I've used it for Rubin project stuff in the validation and verification team and other places. These are nice notebooks for just grabbing, and actually all the notebooks are nice for just grabbing and borrowing code and modifying. Okay, let's continue on. We'll define a couple useful functions here and set some parameters. Right here, we're just basically telling HoloView to use the bouquet environment. It says, hey, you can also use like Matplotlib and maybe Seaborn and things like that, and it'll tell it to output the results to the notebook onto the screen. And we'll also go at some point and show how to output it to an interactive HTML file. So we'll just run that. There is a place later on where it's kind of useful that we convert the data ID for the Kali XP or for the COAD object, COAD image from a Python dictionary to a string. A minor point, but we will define it here, and so we'll just run that. Okay, now we'll do data preparation. We haven't done a whole lot with the butler. Yesterday we're focused on the TAP server querying the database. We have seen use of the butler earlier today in both the previous presentations today. You can sort of view that the TAP server is primarily for accessing catalog data that are in a SQL-like database in tables. The butler accesses this thing. Well, one of the things that process they're usually output is like fits images or fits files or HD5 things. But in the cloud, they're not stored quite like that. So you don't need to know like Unix you don't need to. So the RSP and the butler is stuff, so you don't need to know the location of things in a directory structure. And in some places, there's not really truly a directory structure. It gets a little bit obscure, but the butler kind of solves all those problems for you for accessing, or basically what you might consider as like file contents. So we want to so a certain data set is defined by its configuration and collection. We're looking at DP0.2, the DP0.2 configuration, and per the collection is the processing that is called DP2.2i runs DP0.2, and we call the butler here. And this will take a minute or something, a few seconds. Yeah, it seems long, but it's not so long. Now we're going to grab a CalEXP image. Recall that is the single visit image after being processed and calibrated, and also grab the sources in it. And we need to identify a given CalEXP the image and catalog from a given CalEXP image of a given CCD on the array. You need to specify its visit number, it's the detector number, and the band, and that whole set for the CalEXP is known as the data ID. There's a data ID for coads as well, as we've seen also, and those are made up of tracks, patches, and bands. So let's first look at the CalEXP and grab it using the butler. We'll do a quick assertion that we actually grabbed something, and we'll also verify that the numbers that we put in are also what is in the data set that we brought back from the butler. We'll grab so it'll print out, make sure that these numbers are the same as the numbers, these output numbers are the same as these input numbers. And so we'll run this, and actually this is the one that takes a few. Oh, okay. So so indeed we have the correct the visit number, the band, and the exposure, and the detector output is the same as the input. And then we also want to, so here we grabbed the image from the image. We also want to grab the source tail, the detected sources that are associated with that image. So we grab the source table too, associated with that data ID, and we'll just kind of print out how many sources there are. And we have about a little over 2,500 sources. Oh, by the way, people are curious, this is Larry, one of my cats. And Larry is gonna go visit something else for a while. Okay, let's see. Let's also retrieve a deep coad. So a DP0.2 is based upon the Dark Entities Science Collaboration's data challenge 2 data set, 300 square degree area of simulated sky within the southern sky, and for about 6 years after the 6th year of data. So you basically, the coad is basically the coad of all those data in that 6-year period, in a given tract, patch, and band. So the tract is the kind of the large area, a patch is a smaller area. A tract is about the size of as you'll see, is about the size of tract's fairly big. Patch is about the size of a CCD image, roughly. So we'll grab the coad, the deep coad, and we'll grab some additional information, and we'll look at some tabular information about the visits that went into the coad. So there are 148 overlapping images that went into this particular coad patch. And we get an ID, the bounding box area, the number of good pixels from that visit that went into that coad, and a weighting function, and what filter was used. It's this case is the R band that was used in the version 1.4 of the simulations, or the actually it's version 1.4 of the R band filter, simulated R band filter. And then we can also just take a look and see how many objects are in that. And there's actually plenty more. There's about 40,000 objects in the coad, as opposed to in the Kali the single visit. And you might wonder why. Is it because is the patch much bigger than much bigger than the have cover much that's a coad patch cover much larger area than a Kali XP image, or is it just much deeper, or is it both, or is it neither? We'll see that in this next a little bit later on. First we'll do so we'll just so here we'll just do a generic matplotlib plots of plotting of these images. We'll grab the R index of the coad. We'll also grab whether the R band, we'll grab the R band fluxes, and also whether they're flagged as bad in some way. And we'll also make sure that that the is primary flag is set to true, that after the deblend, it doesn't have any addition, the object does not have any children. It is basically after the deblending, it's the final catalog. And we will create a NumPy mask to make sure that that we're looking at that the is primary flag is true, that the flux is greater than 0, and the flags are all set to 0. And we'll see how many good coad objects there are to plot here. Now we'll just do a simple non-interactive plot just to characterize and see where things are. I won't go into detail here. It's fairly straightforward matplotlib, but here we get a rough idea what is what. So here we see the coad objects are all in blue, the Kali XP objects are all in orange. We see they don't cover the same areas, same spot in the sky, so they're different. They're kind of chosen not quite at random, but they are different areas of sky. But we also see here's a histogram of apparent magnitudes for the Kali XP in orange and the coad objects in blue, and you see that actually the coad objects extend much further out in apparent magnitude. Now, do I trust anything at apparent magnitude 30, 35, or 40? No, I don't. Those are probably just garbage. The real limit for here is probably around 28th magnitude for the coad, and about 25th for the single epoch. So I wouldn't necessarily trust things out here. But anyway, but there are a lot more objects detected in one way or another. Some of them may be, and a lot of probably false positives detected in the coad object, and also but you see where the difference in numbers occur, about a factor of 10-ish, and it's just because they're the coads are just deeper. Okay, let's see. Now let's look at the holoviews. So holoview, okay, so it's kind of an object-oriented plotting package, and which it basically has uses what are called elements, which you can wrap your data around and plot things. it's a little it's a different way of thinking things than with matplotlib, which is more and I have to admit, I don't have my head entirely wrapped around it, but you don't need to have your head entirely wrapped around it to use it. So here we'll use we're using bokeh as the library for plotting within the HoloViews environment. And bokeh is very nice for lots of different interactive work. So let's see. So first we'll look at we'll look at one of the Kali XP and the Kali XP image that we pulled across, and we'll also make use of the AstroPy visualization library to adjust the stretch and the contrast of the image that we're plotting. So the stretch and the interval of what's between the range of color, range of brightnesses that we will plot. So in this case, we will apply an async and z-scale mapping to the data, and we do it this way. We'll create a scaled image by transforming the images, the image data in the CalXP, in the image array of the CalXP data that we grabbed earlier from the butler. And then we'll also do this little this thing. Okay, LSD images, image classes tend to use a pixel indexing convention that differs from what NumPy expects, and also what you generally look at when you're using, like, say, DS9 or other FITS image viewers. So we want to flip things. So right now, most Pine tools assume that the pixel 00 is in the upper left, where we assume that we always assume that it's in the lower left. So we're just going to flip the data array, and we'll use this NumPy array called FlipUD or Flipped, and we'll just change the bounds of things using this using this technique. And then we also want to create some image options for our display, the height and width, what the the x-axis, the padding, the font size, whether you want to have a color bar or a tool, where you want to have the toolbar, if you want to show a grid, and if you want to have a hover tool, you know, using the mouse over tool. So that's what we'll include that. And then we will stick this into the HoloViews image element. Using the scaled image, the bounds that we set up above, the dimensions of which the dimensions which we want to plot, the XY dimensions, and then some various options. We'll do a variation of grayscale, and we'll label things as X and Y, and we'll give it a title, and we'll also include all these image ops here. So this just creates the image. It doesn't display the image. To display it, you use the rasterize command. And we get this. Actually, I'm gonna make it a little bit, I'm gonna reduce the font size a little bit so we can see everything in this one plot. So like I said, you have you have a nice mouse over thing where you get the XY position and basically the brightness value of each pixel, and it's scaled, so it goes from basically about 0.5 to 1. Let's see, this bright star is all 1. You can Right now it's set up for, you can zoom in and zoom out. You can, oops, you can reset it to its, you can reset it. Notice that when you zoom in, it rebins things as you go in. So it kind of, when you get further, oh, I thought it was going to be, oh, there it is. It takes a few seconds. It's a lot of data. So it takes a little while it takes a few seconds to rebin. But it tries to optimally rebin as you go in. Which is very helpful. You can also download the object. You can download this image. You can pan. You can also select a region of interest. And so on. Some nice galaxies and a nice cluster. I can actually stop for a brief moment and see if there's any questions. All right, I'll continue on then. For those who were at yesterday's B session, we showed how to output an interactive image to an HTML file. This is really nice if you have collaborators and you don't want to have them just rerun a notebook. You just want to provide them a nice interactive plot to play with. You can you don't get all the functionality. We basically output to an HTML file JavaScript, and it can do, and the JavaScript can perform as output performs fairly simple operations for detailed operations that are going on in the Python environment. Those are not copied over, so you don't have all the functionality. You get a lot of the functionality from the HTML file. So what we will do here is we will stick this into a file. We'll create an HTML file called mb06a underscore plot1.html in your home directory. And in my case, it goes into /home/Douglas Lee Tucker /mb06a underscore plot1.html. And then you can use this holiday save command to save it. And then you can go to your home directory and you can look down and, okay, you'll see that a few seconds ago, there a nb06a underscore plot1 HTML file was created in my home directory. And you could download it and to your own laptop and plot it with your and open it up with your favorite browser. There's actually a basic browser functionality within the Jupyter notebook also. So you can double click on that. It opens a tab. It's relatively big, so it takes a few seconds to really open it up. I find it takes maybe about 15 seconds or so. It's like an 85 megabyte image, so kind of twiddle thumbs while waiting. Actually, while we're waiting, any questions at this point? All right. This statement, it's taking a little while. We can just wait for a few seconds. Okay, it says, and nothing appears. You wonder what's going on, and then you see, what is this? What trust HTML toggle do? You click on that, and then oh wait, there it is. So once again, so this is just an HTML file. You can post it up somewhere. You can it has the mouse over. You can zoom, although admittedly, you don't have the optimized rebinning as you go in, so that doesn't change. But still, it's pretty nice. So you can select features, or you can do a download. You can pan, and so on. So it's a nice feature for, especially for sharing with colleagues whom you don't want to just say, "Well, just run this notebook." So it's pretty nice. It's nice. And I also encourage people who weren't at yesterday's session to look at notebook 06B, which shows you how to do this with catalog data and having linked plots and so on. That's very nice also. Okay, let's go back to let's see, I was in notebooks. I had my special directory here, 06A. Okay, so let's go back here. Okay, we can also let's move on from the HTML. We can also overlay source detections on that Kali XP from up here. So we can grab, remember, we also grab the source table data. So we can create a coords object which contains the X and Y data, or in this case, it was basically ARIANDEC, Delta ARIANDEC, I think it was, we created here. And then we can generate our own hover tool. There's a default hover tool, which will just basically output a lot of things. You can see that in the 6B notebook tutorial. But here we'll create our own hover tool. And we'll also generate dark orange circles for the positions of detected objects, and we will create that, and then we will again use that rasterize command that we used earlier. But now we have this. We'll now include these options, which include this detection tool with the hover tool, and so we'll run that. You don't need to necessarily understand the details of this, but you can just copy and use it for your own purposes. And you see all the detected objects have orange circles on them, and you have this mouse over with the X and Y coordinate, and you can zoom in and you can grab things and so on. And we can zoom back out. It's moderately big, so it may take a second or two to redo things. All right, let's move along. We're just kind of just showing, kind of give you a taste of what you can do. Once again, you can just always copy things and play with things. And here we're going to do a interactive image exploration with HoloView streams and a dynamic map. So a stream defines one or more parameters that can change over time, and that gets automatically refreshed by the code depending upon those parameter values. So we'll create a dynamic dynamic map with a box stream. So we can explore selected regions of an image, and we'll do this here. We'll run that, and then we will rerun that. We'll rerun that rasterize command. This time we'll include a box select as one of our tools. So it's various tools you can use. Box select is one, and we also include the dynamic map here for that. And so you can run that. Okay, and now here you want to actually select a box. And so you have a box here. It's a little hard to see, black on dark gray, but there's a box in there. And you can get the bounds of that box afterwards. So it runs from about an X pixel digit of 1410. Let's see, it's XY. Let's see. so XY, so it's 1410, 1202 and XY to 2428, 2009 in XY here. And then so you can grab information on the box after, sort of like after the fact. After you select the box, you can do things that, and you can do other manipulations within for that box and the contents of that box. You can also do something with a tap stream instead of a box select. This allows you to click or tap a position and kind of mark a position on your image. So here we'll create a dynamic. We'll basically run code and redisplay the image to produce a white X on that image. So you can see right here in the middle there is an image. I'm going to use my cursor and I'm going to say I'm just going to move that over here, or I can move it over here. So you can use this as an interactive way of marking things. And then you can also find out you can find what the value of the pixel is at that position, and we can so you selected this thing near this actually let's zoom in. Near this galaxy, on the outskirts of this galaxy, and you can find out at the position 35, 93, 1092, the value is 0.69. That's the scaled value, and the raw value that we this is after doing the async and scaling, and the raw value is minus 51.656 EDU. And then actually that is it. And actually, strangely enough, we are we're to time. It's just before the top of the hour. So so let's see, any questions or comments or anything. It's I admit it's some of the details, some of the information is hard to wrap one's brain around. At least in my case, it's hard for me to wrap my brain around, but it is a very useful resource for reusing the code and modify it to your own purposes.
Thanks, Douglas. So you did have a question from Robert Hines.
Oh, okay.
Asked about if the HTML that you made, like the interactive one, if that could be shared publicly, or if you had to host it externally. And Jeff also addressed this question, said that he thinks you need to download it and host it on your own. But yeah, just to see if you have any.
Yeah, you basically need to what we show here. This is actually within the Rubin science platform environment. I don't think you can actually point anyone else to that directly. You have to either send them you can send them the HTML file, or you can and they can open up their own browser, or you can host it on your own website.
Okay, thanks.
Okay. All right. Well, Jeff, take it from here. What's next? I'll stop sharing.
Thanks, Douglas. And the point that Douglas made is a general point about all of these tutorial notebooks that we're showing you, is that you should borrow from them, steal these notebooks, take the parts that are useful for what you want to do and incorporate them into your own. That's what these are meant to be. They're meant to be resources for you. So like I totally am in the same boat as Douglas. I don't understand all of the machinery that makes those interactive plots work, but you can just take it, put it in your notebook and replace, you know, the variables that you're pointing it to. And then maybe once you've used it for a little bit, you'll get more comfortable and start learning how to modify it on your own. So that is a general comment for all of these notebooks that we're showing you. Okay, so we are due for a 10-minute break. And then when we come back, we collected some ideas from people yesterday about your thoughts about things you might want to look into in a breakout. And so we'll come back to that and actually like form into some breakout rooms. If you have a specific topic you want to work on, then you can request a breakout and I can make one for you. Otherwise, we will have a few topics that we can organize around, and you can choose whichever one you are most interested in to go and work together and learn together more details about things. So let's take a break until 10 after the hour. It's 2 after now. So we'll see you back at 10 after. Thanks.